So looking at the answers to the extra practice for this first section on sequences, question number 1 says find the next two numbers in each pattern. So we're literally just going to look for a pattern and see if we can continue it going. So if I look at the first sequence, I have 1, 4, 9, 16. Hopefully you can recognize that these are the perfect squares. So the next one would be 25, followed by 36, because the pattern goes the first term, or n equal to 1, is 1 squared, n equal to 2, or the second, is 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. Taking a look at the next pattern, we're starting at the number 10 and then going down by 5 each time, or subtracting 5. So our next two numbers would be negative 10 and negative 15. The third pattern, we're multiplying by 8, so now I just continue, and to get the fourth number, it's 512 times 8, which is 4,096, and multiply by 8 again to get 32,768. Now the last one is, it's kind of hard to see, there's no straight multiplication. I'm not multiplying by 2 or 4 each time, and there's no straight adding, so I have to look for another pattern. The hint kind of says to look at recursion, and recursion means to look back at the term or terms that come before it. So if I look backwards for this one, I can see that each term is the one that comes before it squared. 2 squared gives me 4. 4 squared gives me 16. 16 squared gives me 256. So now I'm going to square 256 to get the next term as 65,536. Then I square that again to get an extremely large answer. It's 4,294,967,296. So the recursion in this case is to get each term, you take the term that comes before it and square it. And we'll talk more about this later. Question number 2 says find an expression or formula for the general term and the sequences listed above. And our general formulas are always going to use n when n stands for the number of the term. It's also called the ordinal because it orders the term. First, second, third, so forth. So what I'm going to do is just carry over our answers from the last page, so we have them to work with. So the formula for the first one becomes n squared. For the second one, it's a little bit trickier though, because even though we can see that the pattern really centers around subtract 5, and this is a specific type of pattern that you're going to learn more about later, it's not just negative 5 times something. So I have to say, okay, for the first term, second term, third term. So I can't really say I'm starting at 10 and subtracting 5, because that would give me a first term of 5. So I'm actually going to bump it up and say that it is 15 subtract 5 times whatever that ordinal is, because for the first term I subtract 1 5. For the second term I would subtract 2 5s, so my general term becomes 15 minus 5n. And again, we're going to look at a way to come up with a nice formula for any time that there's an adding or subtracting pattern. Similarly, in the next one we have a multiplication pattern. It's a times 8. So I'm starting with 1 and I'm timesing by 8 however many times. But here's where I have to be careful, because for the first term I haven't really multiplied by 8 at all. For the second term I've multiplied by 8 once. For the third term I've multiplied by 8 twice. So whatever my n is, there's always one less multiplication of 8, and repeated multiplications are shown using exponents. So my exponent becomes n minus 1. And now because it's 1 times in front, that 1 really doesn't do anything. So for my formula, I'm going to say it's 8 to the exponent n minus 1. Now, when there's a multiplication or division pattern, this is also a specific type of sequence that we'll learn more about later. Now, for the last one, we will use a recursion formula, and recursion means look back. How we look back is if Tn is a term, Tn minus 1 represents the term before. Tn minus 2 would mean 2 terms before. So it's this subscript notation that tells us to look back. So we discussed this when we were getting the pattern, that each term is the term that comes before it squared. So the formula becomes Tn minus 1 squared. Now, when you have a recursion formula, you always need a starting point, because if I were to try to find T1, or the first term in here, it would become T1 minus 1, or T0, which doesn't exist, because we call these discrete or countable, so we only start counting at 1. So as part of my formula, I have to say where T1 equals 2. So the formula is these two pieces together, and you'll often see it written as T minus 1 squared, that's the formula for Tn, comma, or where T1 equals 2. So when you are giving recursion formulas, whether it's on an assignment or test, make sure that you include all the starting information that is necessary. And now finding specific terms when you're giving or given the formulas is really just substitution that you probably started learning how to do in grade 6 or grade 7. So if Tn is 2 times n plus 1, T4 simply becomes 2 times 4 plus 1. Make sure this 4 stays as a subscript, and there's no math to do here. This is not T times 4. This is just mathematician language for the fourth term, or term 4. So do not do anything with that side at all. And we're just going to do some math here and get that the fourth term is 10. For T9, I repeat the process, but now I'm subbing in 9 for my n, and I do 9 plus 1 first, which is 10. 2 times 10 is 20. The next formula has a little bit more happening, but again, I'm simply going to use a substitution. And I like to write my fractions vertical. It's hard to do that when you're typing in, so they use the slash to separate the top and the bottom, or the numerator and the denominator. But now for T4, the top is going to be 5 times 4 plus 1, and the bottom is going to be 4 plus 1. So that's going to give me 21 over 5, which is in lowest term, so I leave it like that. There's nothing wrong with fractional answers. The ninth term is going to be 5 times 9 plus 1 on the top, and 9 plus 1 on the bottom, which after I do the math gives me 46 over 10. And I can reduce that into lowest terms by dividing the top and bottom by 2 to get 23 over 5.